Namaste everyone, welcome to our next class in current electricity. This is going to be our objective today, a very important objective, though it is going to be a very short one. We are going to study the bridge balance condition in a network that is called Wheatstone network. Now, in order that we understand the working of meter bridge, which is going to be on the principle of Wheatstone network, and in order to understand the bridge balance condition of Wheatstone network, it becomes mandatory for us to recall Kirchhoff's laws. This was done in our previous class, so I have just put it up from the previous lesson. The first law talks about the current that meets at a junction, which says that the algebraic sum of the currents meeting at a junction is always zero. And the second law, that's otherwise called the loop law, talks about the conservation of energy, where it says that the sum of the products of the resistance and current will be equal to the total EMF in the circuit, or the algebraic sum of these two is going to be equal to zero. I had given you one numerical at the end of last lesson, and I had said that I will discuss the answers. And I'm not so sure how many of you would have actually looked into your EduNext dashboard, where I had already posted the solution in the document section. If you had not noticed it, kindly go back and check the document for the solution and check if you were right. Now let's go into the Wheatstone network. So the network looks similar to what it is on your screens now. It consists of 4 resistors, P, Q, R, and S, connected in the shape of a diamond with a galvanometer connecting the points B and D. The source of potential difference is going to be a DC source connected across the ends A and C, as you see on your screens. Now, out of these 4 resistors, the resistor P and Q are going to be standard known resistors. They are going to be standard, they are not going to vary. While R is going to be a variable resistor, S is the unknown resistor. So the moment I say unknown resistor, you can understand what is going to be the application of such a network anywhere it is used in determining the resistance of the given resistor, if the resistance is going to be unknown. And one more condition on using your Wheatstone network effectively is that you have to maintain or choose your resistances in such a way that they are all of the same order. By order, I hope you understand what I mean. The range of the resistances should be the same. For example, if the unknown resistance is of the order of a few ohms, you cannot be choosing your R or P or Q in the order of a few hundred ohms. That means you are crossing the range. So you choose them of the same order in order to increase the sensitivity of measurement of Wheatstone bridge. Now, this is how exactly it looks. PQ, the arm PQ is actually called the ratio arm, because once we are going to go into the bridge balance condition, you will see that we are going to derive an expression for the same. Now, coming back to the mathematics behind the Wheatstone network, we are going to apply Kirchhoff's laws. So let us assume that the voltage source is going to supply the network with current I. What happens when current I reaches junction A? Obviously, since the current has 2 different paths to travel, it's going to branch. So let me assume that the current that branches through AB is I1, and that which branches to AB is I2. Now, what happens when I1 reaches B? Again, let us assume that it moves down to IG, where IG is the current through the galvanometer with resistance G. So let us assume through BC, it moves out as I3, right? Now you can also ask me, why not I2 through G? Yes, you can look at it from that angle too and work on it in that same fashion, you will see that you are going to achieve the same result that I am going to achieve. So let us assume that I2 as it comes here and IG that comes into the junction T moves out as I4 here. And this obviously is going to come out as I by conservation of charges, because there is nothing lost as the charges pass through the various arms of the circuit given. Now let us first begin with applying KCL. So let me apply KCL at B. When I am going to apply KCL at B, we know that the sum of the currents flowing into the junction is equal to the sum of the currents flowing out of the junction. So I have I1 is equal to IG plus I3. I1 is flowing into the junction while IG and I3 are flowing out of the junction. So this implies my I3 is equal to I1 minus IG. So I'm going to write over here I3 as I1 minus IG. Hope I'm clear, children. Now let's look at junction D. So I'm going to now apply KCL at junction D. Again, what do we know? We know that the currents flowing into the junction are equal to the currents flowing out of the junction. So I can say I2 plus IG is equal to I4. Isn't that correct, children? So can I say I2 is equal to, or let me write I4 instead of I2. I4 is I2 plus IG. It's already written. I'm not going to rearrange the equation. So I4 becomes equal to I2 plus IG. Right? So you can see very well what happens at junction C. At junction C, I3 and I4 are adding up. So when you actually add up I3 and I4, you end up nothing but I, because if I'm going to apply KCL at A, I have the current that is flowing in to be equal to I1 plus I2. And if you are going to apply at C, you see that the same current comes out, proving our law of conservation of charge, because it is the same current that has to come out as nothing is lost in the circuit. Now, please keep this in mind. I have I1, I2, I3, I4. I3 is I1 minus IG, and I4 is I2 plus IG. Now, keeping this in mind, after having applied KCL, let us proceed to apply KVL, that is Kirchhoff's voltage law. So let me clear this. I'm moving on to my currents again. So I have considered this as I1, I have considered this as I2, and this was considered as IG. Now I knew that this was given as I2 plus IG, and the current through this was given as I1 minus IG. Now I'm going to apply KVL in a loop. KVL can be applied only in a loop. So let me apply KVL in loop A, B, D, A. Let me apply it in loop A, B, D, A. If I'm going to apply KVL in A, B, D, A, the sum of the products of the currents and the resistances along with the EMF in the loop is going to be equal to 0. So what am I going to write over here? And if I'm going to consider the loop A, B, D, A, that means in the clockwise direction, I'm going to say I1P because I1 is in the direction of the loop, plus IgG because G is the resistance of the galvanometer, minus I2R is equal to 0. Do you agree with me, children? If you remember what we understood from the previous lesson, I2 is in a direction opposite to the direction of the loop. So I'm going to consider the product to be negative. So I1P plus IgG minus I2R is equal to 0 if I'm going to apply it in A, B, D, A. Why is it 0? Because there's no EMF in the circuit that I have considered. So not the circuit, the loop. Now I'm going to apply my KVL in the next loop. That is going to be BDCB or BCDB. Aapki marzi. Let me say I'm going to take it as BCDB. I'm going to again consider the loop in the clockwise direction. Okay, if I'm going to consider it in the clockwise direction, I have I1 minus IG into Q. The other two are going to be negative minus IgG because you are in the opposite direction to the loop. The loop is clockwise while the current is anti-clockwise. Minus I2 plus Ig into S is equal to 0. So these are my two equations that I've obtained using KVL. Now look at the topic of this particular slide, which says bridge balance condition. Now, what is the meaning of bridge balance condition? This particular bridge is considered to be balanced if the potential at B is going to be equal to the potential at point D. What happens when VB and VD are going to be same? That means there is no potential difference across those two ends. Where there is no potential difference, there is no current. That means IG becomes equal to 0. Please understand, this is the bridge balance condition of a Wheatstone network. That is, the current through the galvanometer becomes 0 when the bridge is considered to be balanced. Now, if I am going to apply the condition of IG being 0, that is under bridge balance condition, this term vanishes from my first equation. This term vanishes from my second equation. This particular current vanishes from the second equation too. So what am I left with? I am left with I1P is equal to I2R. Am I right, children? Because the negative on going on to the other side becomes positive. And from the second equation, I have I1Q, and the negative of I2S goes to the other side. I have I2S. I1Q becomes equal to I2S. So we reach to these two final equations when we apply the bridge balance condition on the Wheatstone network. I1P is equal to I2R and I1Q is equal to I2S. Now, keeping this in mind, if we are going to divide the first equation by the second equation, if I'm going to consider this as the first equation and this as the second equation, we obtain the bridge balance condition. I1 gets cancelled on the left hand side while I2 gets cancelled on the right hand side, and the division results in our bridge balance condition, which is P by Q is equal to R by S. This is called the bridge balance condition, P and Q being the standard resistances, R being a variable resistance, and S being the unknown resistance to be measured. So if I'm going to write S from this equation, I can say S is equal to R into Q by P. This is what is going to be experimentally used. I mean, used for experimental purpose. Sorry for the wrong positioning of the words. Not experimentally used, used for experimental purpose in order to determine the unknown resistance of the resistor provided to you. Is that clear, children? Wheatstone bridge balance condition. Now let's move on to the advantages of using this for experimental purposes. You can get an accurate value of the unknown resistor, and if you are going to choose the order of the resistances to be the same, you are going to achieve a very, very high accuracy of your result, because the meter bridge is a highly sensitive instrument that gives accurate results. Now, based on this Wheatstone network is our device that's called a meter bridge, which looks exactly as you see it on your screens. So you have a 1 meter wire. So sorry about it. You have a 1 meter wire of made of an alloy which is either constantan or manganese, and that is the reason this is called as a meter bridge. And all these brown strips that you see are basically copper strips which are connecting the wire to a few gaps, a couple of gaps. So this end point of the wire is nothing but this copper, this screw when it gets connected. Similarly, the other end, the copper strips have negligible resistance. So they are very, very thick. They are thick copper strips, and you know that thicker the area, least the resistance. So we use thick copper strips. This is going to be gaps. So we have a gap 1 here, we have a gap 2 here, and this is a common point of the gaps. So basically, this is either your point B or D in your Wheatstone network. So the D point will be achieved by connecting it with a galvanometer and a jockey. So what's basically a jockey? A jockey is basically a sliding contact. That is why it is otherwise called as a slide wire bridge. You can see the jockey pointed out over here. Generally what we do is S is always connected. The unknown resistor S, generally in the laboratory we fix it over here, and the known resistor, that is the variable resistor, goes to the left gap, but this particular picture shows it in a different way. Never mind, however you connect it, the bridge balance condition remains the same. So you can see the jockey over here. This is a sliding contact which completes the circuit. So the circuit connections are actually given as shown in the figure. Now you can see how the jockey will slide. This is how the jockey looks. Exactly, this is how the jockey looks, and the knife edge of the jockey actually slides over the wire to change the point of contact on the meter bridge wire. So what we actually do is, as the jockey completes the circuit on the wire, so what happens is this part of the wire acts as one of your resistances in your ratio arm, while this part of the wire acts as the other resistance in your ratio arm. So they behave like P and Q, while your R becomes your variable resistor, which is adjusted using your resistance box, and S becomes your unknown resistance, whose value you are going to measure using the meter bridge apparatus. So this is going to be your circuit diagram basically. So what we are going to try and do is to slide the wire for a particular value in your resistance box in order to obtain zero deflection in the galvanometer. So that is why this meter bridge is also called as a null deflection method, because null method, you are achieving the bridge balance condition when the galvanometer shows zero deflection. Now what happens, you are going to measure the length of the wire under bridge balance condition. So let us assume that below the known resistance, that is the variable resistance, you get a length of the wire to be L1, and below the unknown resistance, it's going to be 100 minus L1. That's because we have taken it as 100 centimeter. You can also keep it as 1 meter, and you can give your values in decimals. It doesn't matter. And once I take it in centimeter, I don't have to convert it into meter, because we are going to show that it's going to become a ratio. So whatever is the conversion you are going to get by way of your centimeter to meter gets cancelled off, so you can still work with centimeter. So what are we going to do over here? Once we obtain the conditions of bridge balance, we are going to go back to our mathematical condition. We obtained S to be equal to R times Q by P, where Q and P are the resistances of the particular length of the wire. Now, meter bridge consists of 1 meter wire of uniform cross-sectional area. Let's consider that cross-sectional area to be A, and it is made of an alloy, either constantan or manganese, and let me consider the resistivity of the wire to be rho. And you know that this resistivity is characteristic of the material and does not change if there is no change in temperature. So how am I going to write S now? We know what is the resistance included in our box. And what is the formula for resistance? It is rho L by A. So I'm going to write rho times 100 minus L or L1 divided by area of cross section divided by rho times L divided by A. Now why rho? Because it is the same material. So your resistivity is going to remain the same, uniform cross-sectional area. So area also remains the same. I cancel it off, resulting in my S to be equal to R times 100 minus L divided by L. Is that clear, children? Right? What have we found over here? The resistance across a given length is directly proportional to the length, provided the area of cross section and the resistivity remains a constant. So my S becomes equal to 100 R times 100 minus L upon L. And this is the formula that you are going to use for your experimental purpose to determine the unknown resistance, right? So you will be repeating this experiment for at least 6 to 10 times on your digital platform by varying the value of the variable resistance, and you will average out the 6 to 10 values in order to minimize the error in your result, and hence you get a close to accurate result while you are using your meter bridge. Hope that is clear. Now I will be giving you the virtual lab link of Amrita Labs for you to perform this experiment virtually. Now that is going to be a self-oriented motivation for you, because that particular link has the theory behind Wheatstone network, what we discussed in today's class. It is going to explain to you how you will perform the experiment live, whether you are going to be in your lab or you are going to use the simulator provided in the site. So you are going to read it. It's going to be as simple as we explained it right now. You are going to go to the simulator, try to perform the experiment, and keep your results ready for the further course of action as far as your practical is concerned. So please go through the site that will also be provided along with this video in your EduNext dashboard, and I would very much like you to read through the instructions that are given before you use the simulator to perform the experiment. So we come to the end of this session. The actual outcome is not to derive the Wheatstone bridge balance condition. The actual outcome would be at the end of you finishing the virtual lab experiment to determine the unknown resistance that is provided in the particular site. So please do visit the site whose address will be provided to you on the EduNext dashboard, and do perform the experiment virtually. For any doubts and clarifications, feel free to contact me on my mail, and do the experiment so that you are very clear in understanding the network condition. I will meet you next with another electrical device called potentiometer. Till then, keep studying and stay safe.